This is the first iteration of my audio amp design that is extremely cheap, still sounds good, is super easy to understand, and yet is still powerful and can drive even the biggest speaker you'll find in your house. It's not going to drive an auditorium speaker, some sort of loudspeaker for a production or whatever, but it'll drive any speaker in your house. It can put out watts. My specific design goal is to make it with parts that you're going to have laying around. When you start hobbyist electronics, you're going to get a box of transistors and a box of resistors and a box of this and that. So I'm specifically not buying powerful parts that you'd usually expect to see. I want to use the parts that you have collecting dust on your shelf. So I'm sure this audio amplifier is not going to satisfy any true audiophile out there who really loves their music at maximum fidelity. But like I said, it actually sounds very good. My ear cannot tell the difference. Probably if I had it side by side I could. So anyway, if you're going to criticize this circuit, don't criticize it based on the cheap parts and the simple design. That's the point. If you want the best audio amplifier possible, go buy one. Enjoy spending thousands of dollars. This probably costs $2, maybe $3. This is a mono design. It does one channel. I've already got plans on how I'm going to do the stereo version, the multi-channel version really, and a stereo to mono version, so you can have a stereo signal but still play it on one speaker. It's great for testing speakers or for something that generates audio. And it is the first version, so look forward to future videos with improvements. For now, let's see the circuit. So the first thing about this is that I'm not using any capacitors at all. There's not even a single one, which means that if the signal source has a DC bias, then that's going to be part of the signal, but generally that's not going to happen. So we have our signal source, we'll just say one channel for now, reference to circuit ground. We're going to be using a dual-sided supply. It really is easier that way. If you're making a battery-powered one, just have more batteries and take your ground in the middle. You can definitely make high-quality amplifiers with single-sided supplies. This is just honestly so much easier. So a dual-sided supply, I usually set mine to plus or minus 12 volts. And then the first thing I do is buffer the signal. So I buffer and then I amplify, which is easy because I have the op-amp chips, the real cheap ones, they have two on the same chip. You're usually going to see that. So I'm still only using one chip. The buffer step is probably not necessary, but I wanted to be extra careful in this first design because I'm directly driving the speaker with transistors. I'm not using an intermediary transformer or anything. So I didn't want any risk of me screwing up and feeding, inductive voltage back or whatever. I've already come up with a new design that only uses one op-amp instead of two, which doesn't save parts because there's two on the chip, but anyway. So a very simple unity gain, non-inverting op-amp, just as a buffer. And you could use an actual buffer chip, but like I said, there's two op-amps on one chip, so I may as well just use it. Then the actual amplifying op-amp will be an inverting configuration because it's an audio signal. It doesn't matter if it's upside down. It's just the speaker diaphragm moving back and forth anyway. So what I've done is I've set the volume knob as the voltage divider on the op-amp, the gain control. So the positive terminal, the non-inverting terminal rather, is simply grounded. The buffered signal goes into one end of this voltage divider. The wiper goes to the inverting input, and then the magic happens. It's a push-pull. The output of the op-amp drives both bases of the transistors together. I have two small resistors here. I think I'm using 330 ohms for each one right now. We of course have our speaker. The speaker is driven directly from this output. No impedance matching transformers, isolation transformers, or anything. And then the signal is also fed back through the voltage divider, and there's your gain. So the signal comes in, it gets buffered, then this is the feedback divider that's used to control the gain for the actual amplifier. And that's the entire very simple circuit. When you turn the potentiometer all the way to one side, the gain essentially goes to 0. So the volume is almost all the way gone. And then as you turn it up past unity gain, so you've got 0 volume up to normal volume, and then normal as in whatever the signal's putting out, and then you get crazy gain that, conceptually goes up to near infinity, but what really happens is if you turn it all the way up, you're just going to slam against your rail voltage. And you'll notice doing that, so you just see distortion, hear distortion, and turn it back down. Although, by that point, it should be more than loud enough anyway. So the first note on this design is, like I said, this buffer is not strictly necessary, and what I'm going to do in the stereo to mono version is use a single summing amplifier, which separates the signal and the feedback, so it's not an issue anyway. So one op amp will go away. Another thing is I don't have pull-down resistors on the inputs and outputs. So the future design will have that, where you have a pull-down on the input and a pull-down on the output, so that there's no popping or crackling or whatever when you disconnect the input. When there's no input or output, it'll just sync it. And then when there is, the pull-down will do practically nothing. So one reason you might want these resistors here is for shoot-through, because only one of these transistors is going to be on at a time. But there might be a period in the transition where they're both on, so you want resistance between them so that they don't short. That's actually not a problem. They're not going to short for long enough, it won't matter. Also, notice that the resistors are on the emitter, so they're also serving as base resistors so that it doesn't draw too much current from the op amp. But that generally isn't going to be too much of a problem because the transistors are going to self-regulate a little bit. You could even put them in Darlington if you want, but that's not necessary. You want two, because again, only one's going to be on one time, so one for this and one for this. But also it keeps the midpoint. You want the same value resistor here because it's essentially a voltage divider. So if they're both on at the same time, it'll still be 0. But of course, normally only one is on. And the smaller the value, the better, because you don't want to waste power that could be going to your load. So here's the real magic. I actually use parallel transistors. So let me take this away and show you the parallel setup. This is transistors in parallel. First, why? Because these are weak transistors that on their own would never be able to drive a powerful speaker. They would just fry. My resistors might even fry. So by having them in parallel, they all share the current. Second, by having a lot of them in parallel, in fact, I'm using 8 NPN and 8 PNP, which is still not even $1. They're so cheap. Because you get a box of them. Like I said, you're going to have a box of them sitting around. 16 transistors, I probably got 100 in there that I bought for a few dollars on Amazon when I first started. But anyway, they share the current. So this means that you don't need powerful transistors, you don't need powerful resistors. You use whatever you have laying around. Any power dissipation whatsoever, you can just use more of them. Also, they don't need to be heat sinked because you have more than you need. They're just going to heat sink into the air. They're going to dissipate into the air. You don't have to do anything. You just have it there on the board and you're done. As to how the parallel is set up, I did a video on parallel transistors. I'm going to forget to link it in the description, but hopefully you can find it by searching for parallel transistor. But the idea of it is, parallel transistors each require their own resistor. They self-balance because as a resistor heats up and cools down, the resistor changes how much it conducts. The transistor heating up and cooling down changes how much it conducts. So that can end up with you accidentally having a runaway and one transistor starts hogging all the current and then it burns out and you start burning out one by one. But as the current changes, the voltage drop across the resistors changes. So if more current goes to the resistor, there's a greater voltage drop, which means there's a lesser voltage drop across the transistor, which means less current, less heat. So if the transistor heats up and starts conducting more, then the resistor is going to counter that with a voltage rise and a greater voltage drop, and it's going to choke off the transistor, and the same will happen in reverse. So each of these resistors is having a slightly variable voltage drop as the transistors heat up and cool down that is slightly counterbalancing how much the transistors are heating up and cooling down. So it's a very small wiggle, not enough to be audible. You know, it's just lost in the noise. So each resistor has that role. It also is a base resistor, essentially, because each of these is going to have a slightly different base emitter voltage drop. So that's accounted for in this resistor. Because the output of the op amp is connected directly with no intervening resistors to all of the bases. In my case, all 16 bases, but there's 6 bases here. So it's really easy to hook up. I just ran a couple bus wires and tied them all together in a row. It was so quick. It's not like there was a ton of soldering. That wasn't even the hard soldering. The jumpers were harder. But you just put the NPNs up at the top, tie all the collectors to positive power, tie all the emitters to these resistors. For the PNPs, tie their collectors to negative power, tie them to the resistors, and then all 6 bases tie them together. That's all you do. And then it's just the load is connected through the voltage divider and so forth. I'm sure I would be laughed out of any conference of electrical engineers, but I don't care because this is hobby level fun. Also, I love symmetry. Look at all the symmetry here. It's beautiful. It's so nice. But that's how you wire them up in parallel. You just need a resistor on each emitter. And remember, the NPN goes first and the PNP goes after, because you want the power going from collector to emitter on the NPN out to load, or the current going from the load through emitter collector on the PNP. That's the normal flow of current. So it's backwards from what you'd usually expect. But that's it. Simplest circuit in the world. I'll do a future video on an even better version. Multiple better versions even. But for now, let me show you in action. I have several speakers, including a really nice one for a full stereo system that you're going to love. So here's my little board. I, of course, did it in the breadboard, and it did work, but with tons of interference, so I made a board. But you can at least test it in the breadboard and make sure it works, even if poorly. I'll show you the board after, because it's already hooked up, so I'm going to demonstrate it, and then I'm going to unhook it and hold it up to the camera so you can see. So I use 12 volts and 12 volts, plus or minus 12 volts for a total of 24. The current right now is just feeding the op amps, and it's amplifying whatever tiny noise might be there. But my input is obviously disconnected, as is my output, which right now is just these 2 alligator clips. I'm connected to the left channel here, but it doesn't much matter. So I'm going to use my tablet to generate audio. Into my life, this love up to me. Lovely. So I'll go ahead and plug the tablet in, and now it's detected that it's got headphones in it. So now if I hit play, it doesn't make any noise. So the first speaker I'm going to try is this dinky little one. I don't remember where I got it, maybe out of the spooky breaker box or something, but it's labeled as 8 ohms and half a watt, 500 milliwatts. So I'll go ahead and connect the speaker, and I have my potentiometer as the gain on the amplifier stage. So I'll go ahead and just start turning that up, after hitting play, of course. And so I've started to barely hear audio out of it. It is a weak speaker, but if I keep going up, so right now you can definitely hear it playing. Doesn't sound great, but you wouldn't expect it to. And if I turn it up a little more volume, but then it begins to sound terrible. And what's happening is I've gone beyond the limitations of the speaker. It really just can't handle anymore. The speaker, the op amp, that's all it can give it, and it's slamming against the rails somewhere. But it does work. So let's go ahead and rewind a little bit and pause it. And now let's try this one that I took out of a computer speaker at some point. It's labeled as 4 ohms and 1 full watt. So I'll put the clips on here, and let's get us some gain after hitting play. And now you can begin to hear it. Definitely sounds better. Not great, but better. Let's turn it up louder. So we're getting some decent volume out of it now without distortion. You can see it's using quite a bit of power, relatively speaking. How far can we go? About that far. So there's the maximum volume this one is putting out without distortion. Definitely louder. But what about a real speaker? How about this one? This is the center speaker from a 5-speaker stereo system I've had many decades. That's right, that's real copper wire inside there. This is quality stuff. So let's go ahead and hook this up. And let me preface this by saying, I do have some long wires, and it is causing some interference. Another thing I'm going to do in the future is run the wires a little better, try and embed the wires, separately so that there's less interference, but I'm running the signal and ground and everything through the breadboard, just for demonstration purposes. But let's hit play. And now with a real speaker, let's see what we get. I've barely turned this up, and I can already hear it just a teeny tiny bit. Can you? Maybe, maybe not, but I've barely turned the gain up, and you can already hear it. How about a little more? Oh, that's so much better, isn't it? Just listen to that. In the sky, to you. See? Even with the tiny bit of interference, and if I touch it, it'll clear up a little bit, but still, much more quality. How loud can we go here? Pretty loud. Tiny bit of static from the interference, but I hadn't even gotten halfway with the gain, halfway on this dial. Or I guess, let's see, that's half. So yeah, a little after half. Just a little bit. And it's already loud enough, I don't want to turn it any louder or I'll disturb my neighbors. We'll just do a quick little pulse. And see, yep, we get some serious pulsing before we get distortion there. So cheap, so easy. And it works. I know you may not be terribly impressed, but remember it was still going through a breadboard and this was my first attempt. I did trim all the legs. It looks reasonably nice. But here's the board. At the top, I have all the NPNs. In the middle, here's all the PNPs. The pairs of 2 resistors between each one. And on the back, which you may or may not be able to see, I just have bus wire running across with positive power, with the base signal, and with negative power. And I'm using some solder bridging, but mostly just putting both pins in the same hole. Here I've got my 2 op amps on one chip, my potentiometer, and the rest is just wires and pins. That's it. Such a simple board. I consider it a successful proof of concept. So feel free to leave your ideas and criticisms in the comments. And in the next version, I'm going to have better wiring, pull down resistors on the inputs and outputs, and an even simpler circuit. So until then, I'll be seeing you.